Hey everybody, and welcome back to Algebra 2 Online. So this is going to be the first video in kind of a short unit titled Conic sections right here. And this name, Conic sections, comes from basically I want you to think cone sections. And this is actually like a double cone, right? Like this part up here is basically a cone, this is a cone. And what we're going to study are four graphs, they're not all functions actually, that come from this weird problem where if we take a plane, like I want you to see this as a plane, and you kind of cut across the cone in different ways, you can get different like two-dimensional graphs. And actually only one of them is a function. But there's four of these, and they are what we classify as conic sections because they come out of cutting a cone with a plane. And that seems all pretty weird, I think, and odd that we would care about that, but it turns out that all of these are actually used in a lot of different applications. These four graphs are like very important in just a lot of real-world problems. And so they're also all nice graphs that scale up in dimension really well, like in higher classes, like in Calc 3 and things like that, where you do a lot more three-dimensional graphing. These become like the building blocks for so much other higher dimensional graphs that we see in the world. So they're very good to know. What I want you to kind of pause and think about first is if we do that problem, if we take this plane and we imagine like slicing through this double cone thing, think about what different shapes we could get. So I really recommend you like pause the video and actually like think about it. I'm about to talk about them right now, so hopefully you paused it and think about it. So definitely one of them, if you take the plane and you cut right across, like the cone up there, right? Your two-dimensional, like cross-section would basically just be a circle, right? So if your plane is perfectly horizontal, then you can definitely get a circle. Okay, that's going to be one of them. And kind of similar to that one, if we take our plane and cut on kind of a diagonal, okay, but like don't go through the top, basically, you would get sort of a circle shape, but it would be kind of at an angle and ends up making it into what we call an ellipse in math, but basically just an oval. So you can get this kind of shape, which is called an ellipse. And then the other two ones are sometimes a little harder to think about. If you take the plane and kind of cut through like the end, like this way, then what you're going to get is you're going to basically get like that kind of looking thing, and that would basically be just a parabola. So parabolas are definitely something we can get here. So I'll just do an open up down one. So that's actually a conic section. It's one graph. That's the only one that's actually a function that we know about already. And then the last one is basically if you let the plane go like through both of these, then what you're going to get is you're going to get kind of a parabola shape down here, and you're going to get a parabola shape here. And that is something called literally it's spelled like hyperbola, but it's called a hyperbola. And they kind of look like this. They kind of just look like a double parabola. But one thing that we'll talk about here in a second is that this is actually a sharper curve than a parabola sometimes. So anyways, this is spelled literally like hyper and then bola. So it's kind of like a hyper parabola in a sense. But those are the only four. You can't get any others. And over here I have a picture that kind of tries to show them a little bit better. So you got your circle, right? You got your ellipse, you got your parabola. You can definitely get open up ones and open down ones. And then if you're straight up and down, you can get a hyperbola. And these graphs all show up in tons of different real applications all over. We've already studied projectiles like this. Parabolas, model the path of projectiles in kind of like what we call an idealized system. So if we don't have like wind resistance and a whole bunch of other things, it really does look just like a parabola would. Ellipses pop up in like orbits of planets are ellipses. This is actually a famous building where this is an ellipse right here. It's big in like architecture. The path that we kind of think of as where the electrons move is actually an elliptical path, which is very similar to this orbit idea, but here, a weird thing that's happening actually is the electrons sort of jump from orbital to orbital, so they don't move in the way that you kind of normally think. They don't just actually go like perfectly around, but if they did go perfectly around like this, it would be an elliptical path that they move. So those are a few of those. Circles show up all over the place. The hyperbolas show up a lot of physical places too. So this is actually meant to show a comet right here. And hyperbolas actually have kind of a sharper point, and a comet actually moves on like a hyperbola. So it comes in and kind of bounces around the sun and then shoots way back out of the solar system. And they actually perfectly are modeled by hyperbolas. But these are just a few examples. They're literally all over the place. And like I said, all of these scale really nicely to higher dimensional versions. So the way we write the equation of a circle can scale to a sphere. Ellipses can scale to something called an ellipsoid, is like a three-dimensional egg-shaped thing. There's something called a paraboloid, which is like a bowl. And the way you write the equation of a paraboloid is very similar to this. And then there's something called like a hyperboloid. And that's what this kind of scales to in a higher dimension. But all of these become like the building blocks for a lot of other famous surfaces out there in the world. All right, so today I really just want to talk about kind of how we classify the equations of these four different things. And to start off, this might not seem like we're talking about any one of those four graphs, but this is actually related to one. So basically just in terms of like x1 and y1 and x2 and y2, I want to find the distance between A and B here, okay? And if you haven't seen this before, it really just comes out of a triangle problem, which is why I say this shaded triangle is there for a reason. You may want to use it. So hopefully this thing, you kind of know where this is going, because you should know like the distance formula by now, but just to kind of show you where this comes from. So the distance, this distance AB, you really just do, it's literally just Pythagorean theorem, a squared plus b squared equals c squared, okay? And there's distance formulas that are in higher dimensions too. You can do three-dimensional distance formula, and it basically scales really nicely. In 3 dimensions, it kind of takes this and turns it into more like if I use like x, y, and z. The distance squared is basically like x squared plus y squared plus z squared. And that would basically be if one of the points here was actually at the origin. If it's not, we just have to do a little subtraction in here. But this distance formula idea, distance between 2 points, is another thing that just scales really nicely as you go up in dimension. So yeah, I'm just going to literally do Pythagorean theorem, and C is my hypotenuse, right? That's going to be my distance. So these are lengths of the sides of a triangle. So I'm just going to do like, we'll do BC. I'll just write So we got BC squared plus AC squared is going to be AB squared. That's the idea. So BC is just, like x2 minus x1. What color do I want to do? Let's do x2 minus x1. And then AC right here is y2 minus y1. And then AB, right, is what I want to solve for. So I'm just going to put in AB squared, right? And to get rid of the square, right, we know we can just square root. And that's it. So the distance between AB here is this right here, the square root of x2 minus x1 squared plus y2 minus y1 squared. That's just the distance formula between these 2 points, okay? And that is very related to one of the conic sections, okay? It's related to a circle. Because if you've never seen it, this is the definition of a circle. It's a set of all points in a plane that are equidistant from some center point, okay? So basically it's a set of all these points here, right? Kind of arbitrary xy points that are the same distance, or the radius, right, from the center HK. And so you basically get this by doing just a distance formula. The problem you do, so this right here, x minus h, is this distance, right? And then y minus k is this distance. And the radius is, of course, that. And so it's really just a triangle, like distance formula problem. But you're probably used to writing, this number over here, or this term over here as a number. Like this is an example of like a circle that you should be kind of like familiar with. But, in the last problem, this was basically like our distance in a sense. So this is the distance from the center out to the edge squared, right? And so, just to make sure you can read this right, if this is my equation of a circle, the center is always the HK thing. And so it's kind of like function transformations, like x minus h means you actually shift to the right h. Y minus k means you shift up k in there. And so it's kind of the opposite of these numbers in here. One of them is just 0, though, right? And then the y plus 1 means we're over at minus 1. And then the 36, is equal to the radius squared. So the radius is equal to 6, right? So yeah, you should, if you don't believe it, you should go and plug that into like Desmos, and you can see that these are the two kind of important characteristics of that circle, okay? Parabolas, I'm not going to actually talk about these that much in this unit because we already know a lot about these. I just want to do a really, really quick review. So we've got 3 different ways that we write parabolas that are all written down here. This one is vertex form, right? And it's always the vertex is given by the opposite of this number, and then whatever this number is, okay? This one is factored form. And, the good thing about factored form is that you know the roots, because if you have something like x plus 1, a root is -1. If you have like x minus 3, a root is 3. And so here you kind of you should basically know the roots from the equation in that one. This one, of course, you know the vertex because it's in vertex form. And then this last one is standard form. And standard form, the kind of useful thing is usually using the quadratic formula. Or like a y-intercept, right? Because the y-intercept is always the c value, which you can't do from these ones. You don't just know the y-intercept. but you need to use this form if you ever want to use a quadratic formula, right? So that's kind of where we've seen that one the most. But we will have a day where we talk about circles a little bit more, actually in the next video, but I'm not going to really say too much about parabolas. I more just want you to know that they are a conic section that is part of this group of 4 functions. All right, so this is a very important kind of slide. There's lots of important things on here I want you to be able to do. So this is actually something I want you to actually pause the video and go and play around with. So I really want you to go to Desmos. I want you to type in this, okay? And this is actually kind of our general conic section formula, I guess. And if you type this in exactly this way to Desmos, and you just click Add All Sliders, you'll basically have a slider for every non-x or y variable here. So you should have 4. You should have an A, H, a K, and a B. And if you move those sliders around on Desmos, you can actually answer these questions, okay? This becomes a very important formula just when it comes to what we're going to do next, which is like classifying conic sections. So one of the things I definitely need you to be able to do is, like, we're going to talk about this in a second, but if I give you these kind of different equations, they're not functions, but if I give you these different equations, you should be able to pretty quickly, once you're familiar with how this formula kind of works, tell me which conic section we have here for these two things, okay? And in class, I'll play around with this a little bit and show you, like on Desmos, what I'm talking about here, but it really is important that you spend some time doing this as well. So I'm going to run through these answers now, but I really want you to like try this on your own and make sure that you understand how I'm getting what I'm getting here, okay? So pause the video, plug all this in, add sliders for A, B, H, and K, and move them around and try to answer these questions, all right? I'm going to give you a few seconds, pause the video, and try that, and then I'm about to talk about what you should have seen. All right, hopefully you paused the video and did that. So what I wanted you to see is to get an ellipse out of this, okay? You should have that like A and B are not the same thing, okay? Because if they're the same thing, I guess we can answer this down here. So if A equals B, that's actually a circle. That's what you should have seen. And to be an ellipse, basically both of them also need to be positive, okay? Because a hyperbola is where A and B are not the same thing, again, but either A or B is less than 0. So if one of them is negative, then it's going to be a hyperbola, okay? The conditions that make, so there are 2 types of ellipses, basically, right? You should have seen this kind of ellipse or this kind of ellipse. It's kind of like how there's 2 types of parabolas. And to have like an ellipse that's larger in the y direction, this probably isn't super surprising, but basically the b needs to be bigger than the a. This b kind of is acting as like a stretch factor thing. And if this is a larger number, then it's pulling it more in the vertical direction, and so you get kind of this ellipse versus one like this. If this is bigger, then it would look like that, okay? The center for all of these is HK, very similar to what we talked about over here. The center is always the kind of opposite of these numbers in here. It's really like function transformation kind of thing. And then for number 6 here, there's also 2 types of ellipses you should have seen. So you should have kind of seen that there's 2 types of hyperbolas. So there's hyperbolas that shoot out left and right, like this, versus ones that kind of go up and down, like this. And if you're asking the question, what condition make a hyperbola shoot out left and right? So this way versus this way. It's probably not super surprising. To make it be pulled more in the x direction, you just need the a thing, the scalar with the x, to be bigger, okay? So here, a just needs to be bigger than b. If you have one where it's pulled vertically, the b is bigger, the y scalar is bigger than the x scalar, okay? And the last one is pretty tricky, but if you try and I'll probably do this one in class just to really show you what's happening a bit. But you can use A and B to actually figure out how far the graph is from the center, right? So if like the center of my ellipse is like here or whatever, A and B actually, let's do those in different colors. So the blue and the purple right there are basically linked to A and B. And it's hard to see, and it's the same for like hyperbola or something too. Here, you kind of have one of the measurements that matters, but like on this one, you would have the other left and right measurement that matters. But that A and B, the way you can do it is you can basically square root. And so if you like square root A or square root B, that'll tell you the distance from the center out, right? And B is your vertical one always, and A is your left and right. So like in this ellipse, if you square rooted whatever the B is in this, it'll tell you how far to go out to the edge of the graph in this direction. If you square root the A here, it'll tell you the left and right measurement from the center to the kind of edges out there, okay? Same thing for these guys, okay? So that one's a little tricky to see, but I'll kind of in class go through that one a bit more too, just so you make sure you see it. All right, so when it comes to classifying conic sections, basically you just want to, maybe do a little bit of simplifications at first, but you really just kind of want to think about questions kind of 1, 2, and 4, because a parabola should be pretty obvious, because a parabola shouldn't have a square on both, of course, right? So, if I dropped this 2 here, then it's just a y equals some x squared thing, right? It's just rewritten funny. But parabolas are pretty easy to find, but ellipses, hyperbolas, and circles take a little bit of work. So for ellipses, A and B just have to be the same thing. Or sorry, not the same thing, and both positive, though. That's what I want to say. For hyperbolas, they can't be the same thing, and one needs to be negative. And circles are, of course, the ones where these need to be the same thing, okay? So if I take this first one, okay, there's not much simplifying to do, really. You could just divide 36 and 12, right? And so you could get, I'm literally not going to do anything to that. 36 divided by 12 is 3, right? And then, this 3 and this 3, basically like 1 over A is equal to 1 over B, which is equal to 3, right? So here, they're the same thing, so it's a circle, right? Has to be a circle. The A and the B are the same thing, and I also say, so I want you to classify each conic section using the equation, and then also what is the center? The center is always just the opposite of these. So the center for this conic section is 3 negative pi, okay? For this one, right, your brain might see this negative at first, but be careful, because there's a negative actually in every term, right? And so if you multiply by a negative, then there's actually no negatives around. And so if I multiply by a negative, I would now have positives in every term, right? And So A and B are actually the same sign. They're both positive. And, basically in order to be a hyperbola, you would need one of these to be a positive, and then there's like one that's off on sign in there. But for sure, the A and the B are different numbers. You don't have a 27 here or nothing to simplify to make these be the same A and B values. So basically here, A and B are both positive, but A doesn't equal B, so it's an ellipse, okay? And the center on this one is, again, just opposite of these numbers, so -4 and 3, okay? And that's kind of it. You really just do a little bit of simplifying to kind of take a look at the A and the B values. All right, so the last thing I want to do here is just write an equation of the ellipse that has these vertices, okay? So I'm going to start and just plot all the vertices. All right, so once we have the vertices drawn, you can kind of find the center, right? Because you can imagine like just these two axes, like where they cross, right there, right, would be the center. So the center is pretty clearly, 6, and then -2. And so the graph is also pretty clearly an ellipse, right? Like if these are, the vertices, we don't really need to do other points. We can kind of just try and graph it by like connecting these 4 points with like an ellipse. That's a pretty bad one, but for the equation of it, right, we need to know the center, right, which is going to go, we'll kind of put that in here and here. But then we also need to know these like A and B values. We need to know what to put on the bottom here. Actually, let me go back here. And remember this piece, this is probably the most important little question on this slide. You can square root, like the distance from the center out is the square root of A and B, right? So if that's the case, then, and B is always the vertical and A is always the horizontal. So this distance is 3, right? Because we're going from 6 to 9, right? 6 to 9. And then the vertical one is, what is that? We're going from 2, or -2 up to 4. So that's 6, right? And so B is, square root of B, I should say, is 6, and the square root of A is 3. So B is 36, and A is 9, right? And so then we have everything we need to write down the equation. Basically just x minus 6, all that squared, over A, which is 9, and then y plus 2 squared over 36. We just do equals 1. And if you literally go and like plug this in, this is what we would actually call, this is the standard form of an ellipse. And it's standard form once when this equals 1, actually. So there's other ways to write it. But when that equals 1, that is the standard form of the ellipse. And if you go and plug that into Desmos, it really will graph a much more elliptical looking thing than this. But it will graph this ellipse that goes through these vertices.